This conference will now be recorded.
This is training day 2 of System Architecture Exploration by Nebulous Design. I'm your host, Deepak Shankar. And today's agenda is first and foremost start off with any questions that anyone has on the topics that we discussed in the last session. So if you have any, feel free to type them as we go along so that our engineers could answer the questions during the session or even right now. In addition to that, we had recommended a few tutorials. Want to see if any of you have been able to complete the tutorials, and if you have any questions on them. Now, on day 1, what we covered was we covered the types of models in Visual Sim. We looked at the basic methodology, everything from functional to task graphs, to mapping, to cycle accurate or timing accurate models. Then we studied some of the basics such as traffic analysis, resource and processing. We did not complete power consumption. And then we looked at different types of resources, the time-based, quantity shared-based. We looked at queues, servers, and system resource. Now, today we're going to revisit some of those again. And then we're going to answer any questions on the take-home tutorials, and then go with a discussion on power consumption and on scripting, and then look at how the hardware components, including the semiconductor components, are being used, and then have a discussion around completely custom development. Now, before I start with the power modeling, I'm going to start with a simple model so I can show you how you could use Visual Sim in an application that covers the very basic architecture. So here what we have is 3 separate types of models. These two use queues, and this uses the dynamic instantiation of the queue. I'll talk about dynamic instantiation a little later. But what we have here is a block called the traffic block we saw earlier, and we're using a distribution to generate traffic. The processing of the expression list block right now is not being used for anything, but if you look in the second flow, it selects the right queue that we're going to place the data in the queue block. The queue block has been set up to be able to hold the data. So in this first case, everything is being sent to the first queue. That's why you see the default and nothing is being updated. But here, you'll see that the queue number, which is the field of the incoming data structure, has been updated. Also notice that we are linking this number of queues right over here. If you remember the last time around, all we did was came out of the queue, had a delay, and then we popped it with a const. Now we're doing something different. Here what we're doing is, rather than just popping it, we're also doing some addition tests. We're first checking to see if the queue length, which is the queue is the name here, which is inside of this block, the first parameter, underscore length. This is a memory array or a variable that contains what is the length of that particular queue. And we check to see if it's greater than a threshold, which is 5 here. So if the queue length is greater than 5, we say, okay, we're going to put the full value in here, and then we're going to go through a loop where we're going to send them all out. What this means is I don't send it out as they arrive, but I'm waiting for a bunch to arrive, and then I'm sending it out. So the code here is really focused on checking to see, so we're kind of reaching a threshold and then popping all the items in the queue. Or, yeah, exactly. Now here, same code, but now the difference is we don't have one queue, but multiple queues. So here, again, rather than putting a value 1, we're putting that queue number, we're checking the threshold, and if it is, we're finding what was the length of that queue, going through a loop and popping it out. So if you notice, there's quite a few functions that are described in the script here. One is label : begin, an if statement, a while loop, a send, and some regex or some memory variable functions. We're going to discuss these in more detail further down the session, but just so that you understand how you can start combining the blocks we saw and assemble up a system. Now, From here, what we're going to do is, next step is we're going to start looking at power modeling. How do we enable power in design? So if you look at power modeling, there's a lot of uses for power modeling. You can look at, the cooling cost, you can look at battery life cycle, or you can look at a trade-off between power and performance, like we looked at the model last time on the semiconductor component. Now, one of the things that we learned as we start building visual sim was that go hand in hand, which means that you always will, for example, a dynamic voltage frequency is not possible unless you look at whether the performance is still being met. The other one is looking at SOCs and looking at the architecture comparison based on their power. So if I go at one architecture with another one, why is one of them better than the other one based on performance, but also being below a power threshold? If you remember, we looked at being less than 1 watt of power, and we were trying to hit about 20,000 frames per second. So power is a fundamental research that has to be done in system design. How does power work in Visual Sim? If you look at it, anything is a function. It's an operation. So it can be a delay, it can be an arbitration, it can be some sort of a logic. Every time it goes into one of these functions, the processing unit that executes this function can go through multiple states. So for example, when it's not doing anything, it could be in an idle state. Then when it starts executing, it can be in an active state. And once it's done, it can go into a standby state. So there's really a state machine that manages which state the power is over time. Now, this is our power table block. And what's key is this thing over here that gives you the listing of all the blocks in the model. So if I go into our environment right over here and open up one of the models that I was going to show you today, this one here, and you look at this, there's a lot of different power devices right over here. Anything from processors, RAMs, to buses, to even custom components here. These are not just standard off the shelf, but custom. And each one of them, notice, is a parameter value here. And they have multiple states. So some of them just have these 4 standby, active, wait, idle. Some of them also have hibernation, extended sleep, and also deep sleep. And then here, of course, you have each one of them has clock speed associated with it. Now, when I look over here, I have each one of these is not just a single value, but rather it's a computation either based on a percentage of the active state or based on some sort of a frequency and a multiplier. And some of them may be a combination of these. So these actions, these computation here is what's used to fill up these these cells within this particular table here. So what happens here now is to define the power for any device. You define all the states, and then you define the power for each of the states, either as a single value, like what you're seeing over here, a fixed value, or a computed value, which is right over here. Now realize that if, say, the frequency changes, obviously the power changes as well. So you can actually use this to model LDO efficiency by, here, for example, you can change the voltage, or you can even change an LDO efficiency, lowers the power, lowers the frequency, and you can see what the performance looked like. So that's the basic. The second part of it is the power management, which is really, if I'm in a certain state for a period of time based on some logic, I want to move to another state. So going back to the same model and looking over here, you can see for the there's 3 different power management for just the Cortex M33, which is I go from standby to extended sleep to deep sleep, and deep sleep to hibernation. And of course, this one, this custom component can go from standby to idle. So it's possible for you to describe not just the states, but also some sort of a transition between the states, especially in terms of power management, as opposed to activity associated with the state. For those coming in new, feel free to ask questions in the um, in the chat window. Now, there are two items here, if you notice. One is called power states, and the other one's called operating states. The power states are all the different possible states associated with the particular block. And you can have any one, the 4 that you see here, the default, but you saw in that model, there were 4 more that were added. Now, what are these operating states? The operating states are really about the setup, at least the initial setup, so which is existing, which is what is the state that you're going to start off the simulation with. The off state and on state are associated with the activity. So which state, if you're going to start executing something on this processing resource, which state you go to, and once you're done, which state you go to. The reason that this is important is because depending on the task I'm doing, I can go in and modify this value over here. So it can be active function 1, active FFT, active function 3. So I can go in and make those changes. The reason that that's done is because not only am I looking at if it's active, I'm active for a certain period of time, but rather if I'm active and I'm executing this type of a function, the power is actually very different than if I'm executing a different type of function. It allows me to emulate it. Now, one of the key things to remember here is that the power is not a computed value, rather it's a measured value when something is happening in the system, which means when something is executing, the power is taken into consideration at that point. So it's a very important consideration is that this is not an analytical model, it's a dynamic model that's, as the system keeps reacting or executing, the power keeps changing. The way you can see that is, for example, over here, you can see all these different spikes happening at different times, and then the red line shows me my average value. Actually, it's inverted over here. This should be the average, and the blue is the instantaneous. So what is this showing me? What this is showing me is that I can look at two things at the same time, which is one is what's happening at every instant in time, and what is the average over time. There's also, you'll notice in the model that there are 3 ports. The third one is really the power dissipation port, which tells you what state I'm going to be at every point in time. So to give you an idea of what that means, I'm going to take a simpler model. Right over here. And you see these are and if you run your mouse over these ports, you can actually see what they're doing. So we're going to look at the state change port. We're going to bring in a listen to block, listen to port. That's going to tell you at this time, the power table here got modified, and it was for this device, and it went into off state, and this was the time that was there. So you can see the device state and the amount of power that was consumed for that particular state. Now, in addition to that, you can get additional statistics that are generated here, for example, which is related to, you can get the total, what's the average, min, max, mean power, but you can also get cumulative and average power for each device and have that printed out. So you can see exactly what is happening for each one of those. Now, a number of blocks have power already pre-configured in it. So like some of the blocks we studied yesterday, system resource extend, server block. In addition to that, there's also the hardware blocks, which you're going to discuss today, that are also included. Plus, there's any custom block. So for example, when I go back to this model that we were looking at earlier today, if you look over here, these are all my hardware blocks. This is a fully custom block, and these are using the system resource. So the way I know that is because I can see that this was the architecture name, so that's associated with the hardware. These say schedulers, these are system resource. There's also for the server block, you'd get in a thing that says str, and there's a few other settings. If you want to know more about each of these functions, you can go to the front page, click on library documentation, bring up a window, and from here you can click on power, you can click on power table, right click on it and say open link a new table, and you can see all the details. So it actually shows you the list of all, shows you all your examples, and this shows you how for each type what is the configuration for these and what are the default values. So you can see all of those right over here as well. Now, there's a concept in Visual Sim called Regex Functions. What it is these are functions available for you to utilize either in the expression list, scripting language, or in any of the other parameter windows of a number of blocks. Now, in the case of power, we've got 5 of these. So what this gives you is, for example, this tells me what's the accumulated power for this block. What is the current? What is exactly the instantaneous? Not current as in amperes, but rather the current as in time. And this gives me the details of every single block in the model at that level of hierarchy. Power update says that I can move a power state from whatever it is right now to a new state, especially if I'm doing something custom. And right now I'm in an idle state. I can use this function to say, now move me from idle to a standby state, and it can do that. Power update n is a special variation of power update, and what it does is rather than doing it for a single thing, it can actually do it for a bunch of devices that follow the same naming structure. A good example is the server block as well. Now, the power manager, this is kind of the output you get. A lot of data is available for you for every single block. Now, one of the things that's interesting in Visual Sim with the power, let me go into that one, is you can have what's called hierarchical blocks. So for example, over here, I've got the top level. I go inside. I got something over here with a power table there. I can go inside. I can have something here with a power table. And I can go further down and I have another one with a power table. Now, the reason that this is important or critical is because each one of these levels of hierarchy could be maintained or owned by a different person, or it could be a block that has already been checked into your configuration management environment. So when you're modeling it, you don't want to go in and change the power for modules for those. You just want to drag and drop them and use them. So here, what I'm going to do is only set this to write it out. I'm going to go ahead and run simulations. And then what I'm going to do here is I can see for each of those individual states. You can see this was the first level, that's the second, the third is the topmost. And this one here is the one that has all the information. So it shows me the top level, shows me the level below it, and then finally the lowest level below that. And this shows me the consolidation, or I'm sorry. So this is the consolidation, and then you can see these are the levels below, and then there's a level below that and a level below that. The idea is that you can actually maintain the power for each of the individual states without having to actually having to go in and edit the ones that have already been locked into your particular system. In addition to that, we have something called a power state enable. So when I set this up and I go ahead and run this, in addition to the details that are provided statistically, I can also get stats on what exactly is happening in my particular system. So here, for example, if I look at the DRAM, you can see there's like multiple states: standby, active, wait, and idle. And you can see at each time, in this case, as you can see, the DRAM is really like very busy. But when I look at some of these blocks over here, you can see that most of the time it's in standby, and only for the short period of time it's in active state. So using this, you can actually see what state different devices were over the period of the simulation. It gives you that visibility as well. Again, any questions, feel free to ask immediately in the chat window so that we can answer those for you instantly. Now, one of the key things in Visual Sim is the ability to very quickly create custom blocks. So everything you saw right now was standard blocks that you just drag and drop them, you connect them up and use it. And last time you even saw some of our hardware blocks like a PCI Express, AXI, time-sensitive networking, AVB, CAN bus, etc. There's almost about 75 of those IP blocks already pre-configured. Apart from processors, memories, buses, caches, HBMs, network on chips and things like that. Now, one of the things that allows you to create a custom block is our scripting language. The reason the scripting language is important is it has been built just for modeling purposes. It's not a general purpose language, it's done only for modeling purposes. So if I look at the code in one of these blocks here, let's open up one of these. In fact, the code's right over there. What you'll notice is it's got special functions like get block status, await, which is a blocking thing. It's got the use of arrays easily. And it's only got a few functions like while, if else, and for loops and things like that. So a very, very specific function scripting language that allows you to focus only on modeling and not how to manage all of your other kinds of programming things like worrying about the pointers or classes or includes or defines and things like that. Okay? If you look at the scripting language, it's first and foremost, it's fully integrated into the simulator. What that means is I can actually go in and schedule events in the simulator. I can, use in the block diagram editor, I can go and, connect things to the script itself in just like I was connect any standard blocks. One of the things with the scripting language is that it has its own block called the script block. And you can have any number of input and output ports. The input and output ports are really for convenience. The all input ports are stored in a single queue. I'm just going you can have multiple input queue ports and multiple output ports. The input ports, unlike the expression list block, which you saw last session, where you had an ANDing of all the ports, which means all the values had to arrive before you could trigger. This one here, if as in when the data comes in on the different ports, they get to go be stored in what's called an input queue, and they're stored in the order of arrival, no priority, things like that. Now, it is possible that an out can send connections. The ports itself gets Another thing that you can do, oops. So you can go from a script block to an in block or from an out block and come here. Similarly, you can also go from one script block to another script block. So for example, called def set round robin. So here I can say, this one here, say go to this other block, and it will actually send it over to that other block, and it'll go to the input side of that block. So it's possible for me to do any of these combinations. So it's not just that the one script, everything works within it, but it can go across the script blocks, or it can go from out to in and in to out and things like that. Okay. Again, if you have any questions, feel free to type them in the chat window so that you can we continue to answer these questions as they come along. Now, the way the code is set up is once you go through the input port and you get some data in, there's really three parts of the code. The first part is a really top section of the code where you define all your variables. And then the right below it, if you start executing anything and you say have a while loop or an for loop or things like that, those will start executing without requiring any data to arrive into the port. After that, you can have something called label colon begin. Think of this as your main program. So when something comes in, that's where the code will start executing. So anything about that is your initialization, or you want to set up things like, for example, some variables that are continuously collecting statistics information, things like that. So you can have that before the label colon begin. Now, in terms of port token versus port name as a pointer, there is two concepts. There's a concept called port name, which is, as you remember in the expression list, was an identifier to a data structure that arrived on that particular port. Now, in the script block, we don't use the port name directly, but rather we use a concept called port token, which is a register or a variable that stores whatever is currently executed. Why is that relevant or important? One of the reasons it's relevant or important, and let me just move to another block that actually has some code here. The reason is that when we can have something called a time queue, which is a non-blocking wait, and what this allows you to do is allows you to actually store, like something comes in and it says, delayed for this period of time. While this is happening, another transaction or another request can come in and start executing down. So the current, what is called the pointer variable port token, is now stored over here as a value that is sticking there. Another one of the input port comes in is now the new port token, and that can start executing. So one of the key things is that when it comes to something like a time queue, it stops there, and it has its own delay while the next block can start, or the next transaction can start executing. So this is an important consideration where at any time there can be multiple points at which some of these transactions are stopped within this piece of code. And the one that's currently going through the code line I have the label, and then I've got the sends, and then I've got the time queues, and I got the queues. As I mentioned, the time queue is what's called a non-blocking wait, which means that at any time things come in, they cannot be they come in here, they get delayed, but then another token can come in and continue. When it comes to something which is a wait, it's a blocking wait, which means at that point there's the whole code is stopped. So another token cannot come in and start executing. That's called a blocking wait. Now, outside of that, there's a concept called queue, which is I can take something and put it into a queue with a name, and then the code can continue executing. Unlike a time queue where it stops, the queue can continue executing, and then later on you can take it out of the queue and then start processing. The port token that's going between these two is really the token of the transaction that was put into it. It continues down the thing, and at this point, whatever was originally placed here is the one that's taken out. So this is the basic essence of how the script block works. A number of examples available. The code is also, the documentation is also quite extensive to help you understand how this block thing works. So if you have any questions, now would be a good chance to ask the questions now. Now, having said this, there is also the ability for you to add C, C++, Java, Verilog, Python, all of these different languages. Matter of fact, now we're also adding things like Tickle and JavaScript and a few other functions also to be able to be used within the code here. But for now, this one is our primary scripting mechanism. The couple of reasons for it. One is there's a large number of regex functions. The second one is it's focused only on modeling, so you don't have to be an expert C programmer to handle it. And the third thing is that the code executes extremely fast, so it's been highly optimized. So those are three reasons why you want to use this versus some other scripting or programming language. Now, let's go back and look at some of these things we talked about. First is label : begin. This is like a main. So this is where when a token comes in, that's where it starts executing. Now, within the code itself, you can use any combination of regex or keywords. The second one is the virtual connections, which is what I was talking about, where you can send it to another script or in block, or you can send it to a label in the current code, or you can get tokens from an out block or another script block. Now, parameters, variables, and fields. Same as we saw earlier, parameters of that window can be accessed here. Variables can be defined at the top level. Plus, you can also use your local and global variables, which you reviewed last time around. Now, of course, you can add new fields, you can remove fields, or update existing fields. So just like how you did it earlier in the expression list block, you can do it over here. The other important thing is that the blocks that we have in the model, like queues, system resources, servers, processors, caches, DRAM, you have functions, regex functions, to look into them and extract certain, either you do a take or a remove or any of those kind of things that you can do of the transactions or tokens or requests that are in those blocks. Now, let's look at the functions. The keywords are pretty common to what you'd use in C. So you got if else's, you got whiles, for, labels, switch case, and call returns. Call returns are the equivalent of subroutines. So you have a token data structure comes into a call. It calls a name, where it sends it to a label, and then it executes a piece of code, and then it returns it back to the line after the call. So these are the different types of keywords. Port token we talked about. Port name is, even though we don't distinguish between the input ports, but rather we just put them all in a single queue, we still maintain which port it came from. So when a transaction comes in, depending on which port it came in, you could do something different. So that's one of the reasons for port name to be critical. For example, it can be an input port versus an acknowledged port. So things could be different for each one. T now is a reserved or a keyword, as you saw earlier when we were calculating the latency, is something to tell you what the current time is. Now, The methods are another set of functions that are available to you, which is the, you have the queues, the time queues, we saw both of those, the send, you have the wait, you have something called an event. What it is an event is something that triggers at any point in time, and anyone that's listening for the event, so that can be a time queue or a wait that could be listening for it. When that's triggered anywhere in the model, it can start executing from that point onwards. So rather than putting a time value for a time queue or wait, you can have an event trigger it. So where is this used very popularly? Probably the best use of an event is between, say, a hardware master port and the device, or a slave port and, say, a memory. So here, only when the queue is available, I send an event back to say, okay, now you can release it and start sending the next one. It's not a fixed time, because if the queue is full and it has to wait, it will only after something gets emptied, it can send the event back. So it's kind of a very convenient method to go back and forth. Now, again, looking at those events, Goto is something that you can use it as a jump. You can either say go to 3 lines further or go to a particular label. We recommend not using the number of lines, but rather using a label. Wait, as you saw, can be just a delay value, or it can be an event. Send, as you saw, can be a port, a label, or it can be a virtual. And queues, there are a lot of functions associated with the queue function. So you can either put it in, pop it out, or just take it out. You can get a length of the queue. You can get a copy of a particular position in the queue. You can take something out of the queue, which is remove and not a pop. Pop means it'll continue down the flow. Remove means you just destroy it. And of course, statistics. Time queue, you can get things like length, copy, take, and stats. So you notice here you don't have a pop because a time queue is provided either a time or is provided an event. Conditional statements. So I'm just picking one of them for, so you can see we start with this, we get in here, and then we have an increment. Notice is not a plus, have a plus or anything like that. You actually have to explicitly state this. And you can have a loop that runs for a certain number of iterations or things like that. Now, one of the key functions, there's a lot of regex functions, but one of the key functions you use over and over again is something called get block status. Get block status is where you can have get the queue name, which is over here, and you can say what type of function is it? Is it length, copy, take, or stats? And then you can say what index. So it's the index position. Now, in the case of the queue within the script, there's no index because it's always just a single queue. But if you take our queue block or server block, it does have multiple queues in it. So you can specify which queue you're talking about or dimension that you're talking about. So this will give you the length, or you can get a copy of a particular, the head of the queue, or you can take something out of the queue, the head of the queue, or you can look for just the statistics. Queue length, if you take the name plus underscore length, that will automatically give you the length of the queue. So you don't actually have to do this complex function. You can go directly to the variable that stores that information. So that's another thing that you can do. I'm going to take a quick break if anybody has any questions. Go ahead and feel free to ask them right now. So now what we're going to do is we're going to move to model debugging. With model debugging, there are a number of ways that you can do a debugging of a visual sim model. Now, visual sim being a graphical environment, debugging is actually fairly different from the standard debugging that is available with like a compiler or a GDB or things like that. The reason is because you're actually doing the debugging on a visual manner. So there are, as you saw, we could set up things like breakpoints, but you can also look, and I'm not going to go into all of these. We did see things like animation. We saw the plots, and we saw the listen to port and listen to block. So these are probably the most important ones that can give you the ability to do some of these debugging operations. Now, there's also other things like autosave and loggers that also help you in this particular process. Again, if you have any questions to the debuggers, go ahead and ask the questions, and we'll be very happy to answer those questions for you. Now, one of the things is that Visual Sim is set up to be a multi-user, multi-location infrastructure. So we have a lot of capabilities built in that allows you to seamlessly share across your organization. The first and foremost is something called a database block. So the database is like a lookup table. It can be used either for routing or for communication or for testing or for a whole variety of applications. Like even your traffic information can be stored in the database block. So it's a very important capability that's available for you to be able to take a single model and run it for different iterations. So for example, say I have a gateway and I've got different sequences of inputs that arrive. I can actually have a trace file that can be linked to a database that I can be doing lookups to say, if it is this kind of a message versus this kind of a frame or this type of a formatting, what should I do inside the gateway? So there's a lot of applications that the gateway block or the database block can be used for. Now, another one that's very important is a concept called hierarchical block. A hierarchical block is something where you take a bunch of blocks that are located in the model and then you put them into a hierarchy. The reason that this is important is eventually you're going to have 300, 400 blocks in your model. So rather than seeing 400, you can see like 5 or 6 per level, and then you can put it into a next level, and you can keep having as many levels of hierarchy. And each one of them can have its own set of parameter values. So it's important thing is that anyone can have its own set of parameter values that you could store there. Now, another variation of a hierarchical block is that hierarchical blocks are stored in the model itself. Now, say for example, there's a new bus or a new protocol, say TCP. You do not want to have it as part of a model, but rather you want to have it as a separate entity that can be used by everybody within your organization. So then what you do is you actually save it as a separate block, and then you can, it's called an XML submodel, and then you can instantiate it into all the different models that you have going. So you can actually have that block being utilized in maybe hundreds of different models over the entire organization. Now, one of the key things is if you put that into your configuration management and you finally get to upgrade it, you upgrade the class block, and every model that's linked to that particular component would automatically get upgraded. So it's an important thing is that you don't actually have to go in and upgrade every model, but rather once the base is upgraded, everybody else would automatically get upgraded. Key thing is all submodels or all classes need a simulator. Another variation of this class or hierarchical block is something called a dynamic instantiation. Dynamic instantiation works exactly like a hierarchical block. The only difference is you can set up the number of instances of these hierarchical blocks. So at runtime, it actually generates that many instances. So for example, I'll go back here into one of the models that we were looking at, right over here. So if you notice over here, I had this where I was using the number of queues over here. But here with this one, the dynamic instantiation, if you look inside, the code resembles this first block over here. It's identical to that. But the difference now is that here at runtime, I have number of instances. So when I start up the simulation, I can, I can define exactly which instance I want to have, run through, which means that, at runtime, I can say I want to have 5 instances or 10 instances or 20 instances. And then when it comes in, you can select which instance you want, which is right over here, instance number. And this block will help you select which instance that you need to send it out on. So it gives you the ability to create these different instances, and then you can send data dynamically one or many of those instances. And of course, the other thing you can do is once you're done with this, you can bring it back into a single instance and then continue down the flow here, as you can see over here. Now that you understand about power modeling, the scripting, and also now the infrastructure that we provide, we're going to start looking at some applications of Visual Sim. But before we look at the applications of Visual Sim, we're going to look at a few example systems that we can create. So for example, let's go back into this model that we'll be using. Sorry, wrong one. Oops, looks like I shut that model down. Okay, here we go. So one of the things when we're creating it is the scripting language itself. You can have a scripting language just made up of like 4 or 5 lines, or it can be a scripting language that has like a few hundred lines here. So this one here, for example, is the arbitration or is the master port associated with an AXI bus, which is part of the hardware standard or semiconductor standard library. So you can see here, we've defined all the different variables, all the variables, and based on some criteria, it specifies, sets up certain things. And right here are loops to describe different attributes. So it's creating these additional systems. And then here is a master loop, which is above, if you notice, it's above the label colon begin. The reason is this block here does not require something on the input. So it just starts executing as soon as at startup time. You can set up, in this case, it's setting up the thread slave, so it can capture what's happening in each of the slaves. And it also has things like warnings and add stats, which is another function that's available for these blocks. And here's where we're talking about the throttle with the event name. So if you remember, we had this thing which you said that, the wait or the time queue can wait on an event. So this one here, it checks to see that event name field is there. If it is there, it goes ahead and goes through that event process. If it is not there, then it just ignores the event process. So it doesn't actually generate an event. So here's where it actually generates an event right over here. So a variety of these kind of functions can be incorporated to start building up your extended code right over here. Now, before we get started in looking at more detailed models, we're going to look at failure analysis. So in this particular case, there's a variety of failures that can be associated with the model. For example, if you noted in the power, we talked about where the power value keeps going down. As a result, the frequency goes down. So it's kind of like directly linked. Or if the voltage reduces, the frequency reduces as well. That is a type of power/hardware failure. Other failures are where I've got like 3 cores and over time I now only have 2 cores. What happens? Or I get incorrect packets coming in on a particular link. Say I got on my CAN bus and I get some data coming in and it doesn't have the right CAN IDs. So that could cause a failure on the CAN bus. So how do we detect that and remove that out of the network? So you can have network type failure. So a variety of failures can be generated in Visual Sim. Now, another aspect which we looked at earlier, which is about a functional diagram of a radar system. So in this case over here, you can see that this is the details of the radar system. And I'm going to go directly into the radar model. So this one here is the radar system. So you can see you start with an ADC, which is really a traffic generator to emulate the analog side of the thing with an ADC clock. And then you have a series of things that are happening. So for example, over here, if I go to function F3, you notice over here, depending on which mode of operation, so it's task ID and mode of operation, I select here which case I want to go to. So it'll either send it to the first, second, or third mode of operation. And right over here, each one does something different. So for example, here I take the first 400, then take the second 400 bytes. While in this third mode of operation, I launch the M2 and I distinguish it by the dispatch PRI, which is one of the fields of the incoming data structure. Here, if I go into this third case, all I'm doing is I'm doing a transpose and then I'm doing a DMA of the entire matrix. Here I'm doing small pieces. Here I'm actually transposing one row to one column and then sending out the entire matrix. So I can actually put in that level of detail with these basic building blocks. The second piece of what I can do here, this is the pure, we call a functional model. So it just tells you what is the sequence of things that's happening. Associated with it, I can have a dispatcher that tells me how I want to map each function to the actual device that's going to be executing it. Now, why is this critical? The reason it's critical is that, if I go open, so if I open this, what you do see is that there's a lot of different setups, so function ID, task ID, dispatch CPI, dispatch PRI. These four elements determine where I'm going to execute it. I'm going to put on FPGA or gigabit Ethernet or processor, which core in the processor. It's going to select all of those things based on these four criteria. And also each one of them has their own right case. Right now, everything is of priority 1, but I can have each one being associated with different priority. So when requests comes in and they're sent to a common structure, their queues will get reordered. So I can actually map different functions onto different cores or different processors or different modules. Now, one of the things that's critical here to consider is the fact that I can have, depending on what the block is doing, it might send it to a different core or to a different module. So it's because it's not just based on the function, but also based on modes and other attributes for it. So I can have a very complex mapping from the behavior to the architecture components. And notice here, we're using the expression list block, we're using the in and out blocks, we're using the traffic generators, and we're using mappers and the system resource. So if you notice over and over again, we're just using the same building blocks to assemble up the whole system. Now, a second aspect, which is comparing different architecture options. So I have, in this particular case, I'm mapping it on the left-hand side to processors, on the right-hand side to DSPs. I don't want to compare what my timing diagram is, compare when it was executing and what's the effective throughput. So notice how the processor actually has a pretty flat throughput, while this one the DSPs keep varying over time. Now, what you can also do is you can map individual functions to hardware components. So here, for example, on the left-hand side, we're mapping to a Mercury computer, while on the right-hand side, we're mapping to a DSP-based system. And here is the block diagram for the Mercury versus the block diagram for the DSP. Now, those were using standard hardware components. They were not really anything custom or things that we're just using an off-the-shelf box trying to see how we can map them in. Now, here's a case where everything is custom. It's an SoC, a very power-friendly, extremely low-power SoC device. And we have a lot of IOs, a lot of memories, a lot of processing that takes place. And then, of course, there's DMA that takes place within the block. And we actually modeled that by what are called hierarchical blocks. Now, of course, these are standard blocks in the library, they're classes, but you can see all these green blocks represent different hierarchical blocks with different values. Also notice there's some coloring. For example, over here, these are green, these are blue, some of them are blue. So you can actually indicate either, what's the power going through it, or, what type of data is going through it. So you can use this for presentation purposes. So that's kind of an important consideration here. Another variation of this same thing is looking at network on chip. Now, why is this important? The reason is, if you saw the earlier ones were buses, switches, controllers, here we're using more of a network mode. There's a traffic generator that's sending data in. Based on a routing table, it's going to be sending it to one of the outside ports, either to a local device or to one of the other ports, and it's going to keep going down the network. So you can actually model a complete network that's either a card network or it's within a chip itself. And of course, now we're looking more at a multi-bus SoC, which is where we have like multiple buses, there's processors, there's on-chip memory bridges, and they all get connected like this. So you can see the block diagram and the associated model here, and you can also see the DMA operation. So now what we're going to try to do is just show you how we could assemble up a simple model. So we'll start with this. As you saw earlier, we're going to put in a digital simulator. We'll just say we're running it for 100 e minus 600, 100 microseconds. We're going to bring in a traffic block right over here. And then we're going to bring in a block for hardware setup, which is essentially an interface block that takes care of all the connectivity between this and the rest of the system, which is the hardware system. Now, we need an architecture setup because we need something that handles all the routing between all the hardware blocks, plus it maintains all the statistics. What do we have? So here, rather than using header, we're going to use something called processor DS. Why is processor DS important? Processor DS is important because this has all the fields that all the hardware blocks require. That's something that you could utilize. Says fixed, and we say e minus 6, so every 1 microsecond. Now we need to do some setup. So we need to like, for example, specify, let's say this is a camera. We say the destination is an SDRAM and it's a type read. And we're not going to do anything with process, so we're going to ignore it. We'll say it's 256 bytes. Say priority 1. And we'll say we're not going to worry about addresses. So it's got that connect take block. And we're going to connect the DRAM block on the other side. And we're going to set the name over here. We're going to make this a 16 byte. I'm sure that's what the thing, we'll make this 16 byte as well. We'll just call it an axis. So now what we've done is we've connected a traffic generator to a device interface, to an axis, and to the DRAM. So we got something where they expect us to save the model. We're going to go ahead and save the model. Okay, so now we're going to go ahead and run it, and we're going to try to track down to see if the model is working correctly, if there are any errors, any of this. So we did get an error. So what the error said was that AXI master 1 did not find, so master 1 would be the first master here, did not find a slave named SDRAM on port 1 from source camera. So what we need to do is we need to go and configure this block. First and foremost, we'll say there's only one master, one slave, and we're going to give this device a name. So we're going to call this SDRAM. Same model, we're going to go ahead and rerun it after fixing the error. Okay, now we know it ran, but we don't know if it ran correctly. So a couple of different things we have to do. First thing is we're going to connect this right over here. So we're going to see what the output was when that finished. So here you can see I've got, oops, sorry about that, give me 1 second. So as you can see, we came in bus master 1, came out on slave 1, came to DRAM, came out of DRAM, through the AXI read data channel, came data channel, came out of the data, and then came out of the AXI master 1. So you can actually see what is the sequence that's happening and what's the value of what time it arrived. Plus it shows you your latency and the throughput of this particular component here. I'm sorry, for this particular transaction. So now we know that the sequence is correct. So that's one positive thing. The other thing that also can happen is that you can now start doing other types of analysis. So for example, here, I can bring in another text display, plug it in here, and I can look at statistics. For example, I can see, what was the read thresholds, or how much of the reads, what was the usage of the read buffer, and then what's the stats on each one of them. What's the timing, the occupancy, and the delays. Similarly, what I can do is I can also set up what are called timing diagrams. In this case, we'll just focus on the AXI bus and the DRAM. So you can see now that we have the DRAM activity, and then we can see that there's a read process that's happening right over here. Now what I can do is same model. What I'm going to do is just swap this one out. I'm going to replace it with a PCIe block. Exact same thing. We're going to call it PCIe. We're going to say number of ports is 1, 1. Of course, we have the number of lanes, which is 16 bits. Max payload size, we're just going to leave that. We're going to set this to be Gen 3. Number of retries, which is fine. And of course, remember, we have to go update this one here because we have to specify what is the device that it's connected to. Okay. Same model, all I did was swap out the the AXI bus for a PCIe, and you can see you get the activity on the slave port and on the master port. So we had only one. We can see that. We can see what the utilization is, which is hardly anything. But what we can do is we could try to maybe increase that one. So what we can do is we can say 0.2 e minus 6, and the data size can be 1024. So now we're going to go ahead and rerun the same model. Now you start seeing a lot more activity. So we're like at 43%. As a matter of fact, you can actually see that the block is quite busy. So you can see the master port, and that's when the slave port, the data returns. You can see exactly what is happening. And plus, you can see right over here how the hardware block is busy. So what do I do? I had analysis, I had the hardware, plus I had any of the memory devices or other peripheral devices. So using this process, you can actually assemble up your full system, and that way you can start building up the rest of the area, just like in this other model here, which we were looking at. Here, which is, we started off with something small, but now we can start seeing this processors, ROMs, flash RAMs, S4, and there's a memory controller with the RAM, and then there's CMAX that go out to the external APB bus to an external set of peripherals. You have your own DMA, so you have that one also to be. A lot of the newer systems will have processors and GPUs built into the same. So you can evaluate some of those as well. So this is in a nutshell the remainder of the training. I'm still around to answer any questions that you might have, but hopefully this provides you the starting point on how to start using or how to start working with Visual Sim. With this, I want to thank all of you for attending this training class, and hopefully you have your software all downloaded and starting to build models using the software. And there's info@mirabusdesign.com where you can actually start getting help as well. So now, if there are any more questions, our application engineer is available to answer those for you. Also, you will be getting a copy of the presentation and the video link to the model as well. I'm sorry, to the presentation as well.